All right, so Alex Merose, privileged to have you on again. This is the third and final part in this series about, or building up to Open Athena, of which you are a member of the founding technical team. So building on the foundation that you've been laying to do with physics-based models, numerical models, and then machine learning-based / AI-based weather prediction models. We are all ears for what this builds up into in terms of Open Athena. So yeah, take it away.
Thanks. Yeah, I feel like in the previous two episodes, I guess now, I've laid a foundation for what's going on with these like foundation weather models. And I guess I wanted to do in this last, kind of point, make a point about like the system characteristics of these models and maybe how we can rethink how to approach building them. So, this last section I call foundation models a new type of system, and I'd like to explain what that means a little bit. So let's consider I helped make MetNet3. This is a AI weather model that is a neural nowcast. A nowcast is a type of model that is a short-term weather prediction. It will basically tell you if you need to bring an umbrella on your commute based on what you look up. And in that sense, that you get forecasts.
That's all I ever care about with the weather app on my phone, by the way. So perfect.
Cool. Well, it comes up on the Google search results. If you Google the weather in your location, sometimes it'll show you this if it has that information or if it's the most relevant. And the idea is we can give you like a little text bar that says it's going to rain in the next 15 minutes for 2 hours at this very precise location. The model itself, it has like a couple kilometer resolution and every 2 minutes, something like this resolution, both in time and space for precipitation, which is one of the hardest things to forecast. Nowcasts are separate from medium range forecast. Medium range operates 3 days to 2 weeks. A nowcast, it's a really perfect case for machine learning in the weather because you produce machine learning is a good fit because it requires you to simulate a forecast or produce a forecast in faster time than it would take to simulate it using traditional NWP. So it's a really good fit. And one of the features of MetNet3, I think that's really great, is that it's a probabilistic forecast. It means that you get a probability output as opposed to a direct prediction. And usually it requires you generate 50 to 100 or more forecasts to get a measure of uncertainty in a forecast, and we can do it just in one ML model. So it's really great and useful for really everyday use of predicting the weather. And if you look at what it took to make MetNet3, you kind of see a diagram like this, where you have historical data and real-time inference data like radar satellites, the surface of the Earth, feeding into the ML model. You need a lot of historical versions of all of that data in order to lead to the training process. And then it produces an inference. An inference in this case is a short-term weather forecast or nowcast. And you may, if you wanted to, in theory, you could, if Meta was open source, for instance, fine-tune it and create a local weather model. I think we're getting to the stage where more and more places are creating local weather models. Recently, this Chicago and farmers in India came together to convert neural GCM into a local forecast for farmers in the Indian subcontinent. For example,
this is a link to the previous podcast guest about flood forecasting. Aham Ansari. Okay, glad you could continue that thread.
Totally. This process looked like a process called fine tuning, where you take local data and you retrain, or you take a base model and you retrain it to make it specific, to make it useful in that particular area. And then you can predict local variables or things that are locally relevant to you. I have a picture of strawberries here because I live in a small town called Merose, and it's where one of the large strawberry fields grown in the state of California are all grown. We're in the Pajaro Valley, and it's a historic immigrant community in farm country. And strawberries are one of the main crops that we grow, and they're also really sensitive to the particular weather conditions, like the actual days where you get like a certain amount of cold or rain. Makes a big difference in how you grow strawberries.
Is that where Driscoll's strawberries comes from that we buy in Costco over in Atlanta?
That's right. You're coming from my neck of the woods.
Amazing. Wow, we've got a connection there. I wanted to also just show that I've been paying attention to the last episode where you said that the latest development from intervention by machine learning people, I will say, was that medium range forecast went from 2 weeks up to of the order of a month. Is that the case with MetNet 3 as well?
I haven't plugged into the MetNet team. I think they have been focusing on scaling to more places rather than scaling across larger time horizons. So recently, the team MetNet was, while I was working there, it was only serviced in the U.S. and Europe, they're leading to move to a few other countries. MetNet right now, like one of the next countries they launched was Africa to provide like a really highly accurate forecast in a data limited region was like a really huge technical achievement for machine learning. And now I think MetNet, the model, is a global forecast. People who are live in data limited places that don't have the physical infrastructure of sensors that exist maybe in the US and Europe now can get to the best of our ability to estimate, let's say from the raw sensors of like satellites, but with like very sophisticated neural networks, get really useful practical information to make decisions in their lives that matter.
Okay, there's another connection there as well to a former podcast guest, Fathom, which was bought by Swiss Re in the past year. They also made a point of underserved areas and that they offered unique insight there. So yeah, interesting that others are also taking an interest in that. So yeah, good to hear.
I appreciate so many guests are talking about this because I think it is really important that democratize is really thrown around left and right. But I think this is the hope that you would have for like this really sophisticated technology that it would give people information and choices where they were previously out of reach. Due to like so many. Well, I won't get into the beginnings of it. I'll refrain from being political or anything like that, talking about world history. But anyway, this kind of diagram here, like I liked looking at MetNet in particular and like how it could be used to fine tune it to like help particular regions as kind of like a high level understanding of the system where you have like these kind of, well, I call it like four main components where you have training a model where you can get Earth data and produce a model. Inference helps you get those things and also with the model produce a forecast. Fine tuning it, you kind of retrain your model a bit, maybe just like the last few layers, and you can make it really specific to things that you care about. If you take a 10,000 foot view and you look at these system components, that this is maybe pretty normal in a lot of foundation models or ML systems. To me, this reminds me of another entire system and software that's really commonplace. To me, this looks like a database. And the way I think about this is, you have historical data and local data. Those are like tables of large amounts of data. Training to me is kind of like building an index. It's a way of making sense of the data in a way that it's like really appropriate for querying. The ML model itself is kind of like a new sophisticated query engine. And inference, like a weather forecast, is kind of like a query. And in the process of fine tuning the model, it's kind of like you're re-indexing or re-massaging the data in the tables. And maybe updating an index could be making a forecast. And once I kind of put this connection together, I couldn't really not see the parallels between machine learning models and databases. And I think it's a really apt description to think of ML models as databases, primarily because most of the complexity of building MetNet wasn't in the creation of the model itself. It was in the assembling of the data set that spanned the entire Earth of all the different data sources and different data modalities. MetNet itself, it's like a UNet. A UNet is a type of neural network that was first created for medical image segmentation in like 2016, and it's kind of taken the world by storm. It uses a mixture of convolution and transformer-based architectures for those who care. But at the end of the day, like MetNet itself, the ML model idea wasn't relatively new. It was the thing that worked the best. What was really innovative, I think, about the system of MetNet is the assembling of a global data set to make sense of the world and to make sense of weather variables, combining Earth observation to simulated weather data.
There we go.
And
I think if there's a struggle within the audience to understand what you're talking about, at least most people understand what databases are. So I think this will help as a ladder to climb to understand. So yeah.
cool. Well, my main point, and I think this is the big point of a talk I gave at Cloud Native Geospatial, is that I believe that foundation weather models are differential databases. And I'll be careful. I'll take care to explain the term differential, but I think the main difference of an ML model from a traditional database is this idea of differentiation. And one perspective on what ML has done to weather is that machine learning has turned weather forecasting from a batch job run on supercomputers into queries on the latent spaces of data. So like neural networks have their own concept spaces, which we call latent spaces, or like latent means unobserved, and that's why we have the term latent spaces. We like, I guess like this kind of diagram here, to make a forecast now, we really are just kind of like assimilating or making analysis or aggregating raw data more so than we are doing what we were doing before, as I explained in the last podcast, maybe as the listener might know elsewhere. Weather forecasts require simulating physics, forward and backward in time, and that this is just a totally different entire process. I think it's such a significant step change that it should make us reimagine and recharacterize what these systems are. And I like thinking of these systems as foundation models, foundation weather models in particular, as like almost like a new type of database technology. And I think you might be wondering, what do I mean by differential programming? I can imagine that's like the next question that you and your listener might ask. Well, I'm happy
It
to
was
talk
definitely
about.
on my mind, of course.
Yeah. So
Took the words right out of my mouth.
right, yeah. So in programming, programming is traditionally made up of two components. There's data and code. And data here, like here's a NumPy program, or maybe a JAX program, where you can create an X and Y data set that are full of random numbers. And that's what like a program expressing data might look like. Other times data might just be importing something from a file format. Code, we can traditionally think of as more like functions on data, but they're things that take in data and mutate them or modify them and return other forms of data. Machine learning is a weird case where it's kind of like the combination of data and code. I think that's how I would characterize machine learning. And what machine learning really is at the end of the day is looks kind of like this line right here, if you can see my cursor, where you take an initial amount of data and then you treat the function itself as a form of data, that these are weights that in the ML algorithm, you end up updating the weights to. And often what machine learning looks like in the case of a neural network, is you take a function and apply it over and over and over again until you get an end result. And then what you do is you have this kind of meta algorithm where you update W0, W1, W2, independent of, you don't update X, the input data, but you update the parameters of like the solid function, which gets a blueprint. And you basically have a function that is learnable or mutatable. The core capability of a programming language that would make a function learnable in this way, especially in a neural network, but I think and true in all of machine learning, is this idea called differentiation. And a differentiation is like what you learn in calculus, like the ability to take a derivative, but it's relevant to machine learning because it is the mechanism we have in a programming language to get a like magnitude of error as a feedback signal when training a neural network, and when using the process of machine learning, when the actual routine of machine learning really involves guessing and checking and figuring out how wrong you are. That the core capability that is missing is differentiation. Andrew Karpathy, he's really a great leader in the machine learning space. He's worked at Tesla and OpenAI and a number of other companies, and he does a lot of, even when he was a PhD student at Stanford, he did a lot to democratize access to machine learning, to like make it way more accessible through his writings. He talks about like software 1.0 versus 2.0. And in 1.0, you write a program that maybe looks like here on the left. Software 2.0 looks much more like this ML case where we start with an initial program, and then through experience, like by feeding it data and through this routine that I've described in machine learning, you like optimize the program to be the best possible version that it could be. That I think is the missing capability of in databases in general is the ability for programs to optimize with experience.
I like, again, I think in the last episode I used the word whimsy, or throwing spaghetti at the wall. I guess as a rank outsider here looking in, I just like that there's this shift away from a deterministic approach, the arrogance of knowing everything as a physicist or a mathematician. It seems like there's a bit of humility involved here, where it's acknowledged that learning is at the core of things. The data in the code is just serving up learning iterations. And you said it's all about checking the deviation from what's known to be true and what these models and code, or data and code, output.
It is, yeah, there is a lot of humility there too, where it's like, we don't know the physics as good as the data does. We just need to get a system that's sufficiently able to cover every type of operation it might be doing under the hood. Like, let it figure itself out. We'll just give it what it really needs to care about, which is the actual ground truth, the actual, raw data. I appreciate the result here, humility.
Yeah, is the result here that actually a machine learning approach will take us to physics that hasn't been understood?
Yes and no. I think I've explained this in a previous presentation. I think a limit of machine learning is that it usually is a big black box. We don't understand exactly the mechanism at a high level. Like, we understand there's a differentiation happening here, and we update these numbers, but we don't understand the higher level of analysis of like how they're working. I think I mentioned in a previous recording that maybe it'll lead to that really deeper understanding through things like mechanistic interpretability. If we can really like move these models into a format where we can interpret their reasoning, their methods of reasoning, then yeah, it could lead to a new understanding of new types of physics or phenomenon. I think in the short term, though, we have a decent understanding. What we lack is like performance. We lack the ability to predict things that are incredibly hard to predict because they are just fundamentally a really difficult computational challenge. They're really our methods, where we totally understand them, are really sensitive to error and accumulating error. But machine learning models, because they're so spaghetti-like, and we just let them have a really good teaching signal, they tend to be really robust to even messiness in the data or messiness in the mechanism of creating approximations.
I love this. It's almost like by loosening your grip, you enable an answer to arrive in a different way. So yeah, nevertheless, you get to a robust answer. So yeah.
I should say that there's a whole world of PINNs, or physics-informed neural networks, or physics-informed machine learning, that maybe would challenge my like totally stick to the wall spaghetti style of differentiable programming. Like, I say differentiable programming.
I take responsibility for that characterization.
No. I mean, I think it is. I think it is really accurate to describe what pure machine learning is like. I think that there are a lot of really cool. There's really excellent work being done in physics ML hybrids and neural GCM from my colleague Stephen Hoyer. It uses a dynamical core at the center. It uses differential equations, kind of like that Lorentz system that I showed you before, but it fixes a lot of the problems with those methods by having a neural network layer on top of it. And it therefore, like, we can understand it really well, and it can get the benefit of this ability to like understand data like really well and be robust to data. So I think those approaches have a really promising future for sure. I'll move on. I guess if ML models are databases, then I argue they should be built like Postgres. And Postgres is a open source database that has basically taken up the entire database world by storm. Postgres, we used to talk about like databases like Oracle in like the 90s, and it used to be, Microsoft SQL Server used to have a huge amount of market share. Now, if you look at the ecosystem of databases and like database startups, they're ultimately all like, most of them, or a great share of them, are just modifications on Postgres, that particular database system. And I guess I argue that machine learning models could be built in this way. So this is where I want to transition more into what Open Athena, one of the projects that we do at Open Athena. So recently, Open Athena has partnered with Stanford University and their Center for Foundation Model Research. And they have one of our official like primary projects. It's kind of a peculiar domain of science, but of natural language processing is the project Marin. Marin is a totally open large language model that has an open development process. That means that anyone, based with an internet connection, can see every step of the process of building Marin and also learn their successes and mistakes totally transparently. And like they've been really public about a lot of mistakes that they've made and had like postmortems with turn by turn like errors that they hit left and right. And it's like incredibly refreshing to see ML models be developed in that way. And I guess the promise of developing ML models like their Postgres or like their open source databases, I think the thing that I'm most excited about, like borrowing from the idea of Postgres, it is an open, almost like it's an open source database, but it's a community of developers that have built and made different components of the database way better. And it's designed in a way that it can be extensible, where you can, like some person building a new part of the database over here can like lead to an improvement to people working on unrelated things over here. And I think what's really exciting about Marin is that this is one of the very first, maybe the first like machine learning system to do this in large language models or for machine learning models. Do you have any questions or anything right here? I'm happy to continue and explain more about how Marin works.
No, I'm conscious that we've got 18 minutes left, and I want to provide a pathway for you to get to the end.
You can. I could be a little late to my meeting too. If you have questions, I'm happy to hear them.
Okay, no, I think this is great. I mean, so a big emphasis of geospatial FM is, yes, broadcasting, hence FM, but also foundation models. So this is exactly, we're all ears to hear more about Marin and what's flowed from there in terms of Open Athena. So yeah.
Cool. Marin has kind of like a 4-step development process, and I think maybe it helps to be on like their Discord channel. But if you were just totally a curious, excited person on the internet wanting to make better ML models, this might be how you would do it. So like you write a GitHub issue on their GitHub project that you can find. The website is marin.community, and that would lead you to a GitHub project. If you have an idea for an experiment to make an ML model better, to work on a new type of data set, you pre-register what that idea is. I think through communication with the development team, it eventually leads to a pull request where you launch your experiment, or you figure out how the experiment fits within the framework. Should it pass all of the checks and tests and it's ready to go, it'll go on successfully larger runs of experimentation, where maybe it'll start with a small amount of compute and a small amount of data, and then like get progressively bigger. It could make it into a whole like hero run, like the final model, if it's like really quality or leads to a significant improvement. But while it's leading all these different levels of runs, you have a weights and biases. W&B is in machine learning, it's like a tool for tracking ML experiments and seeing how well or poorly they're performing. So it really is a totally open development process that lets anyone with just an idea or willingness to help or contribute like make a difference. What I find really exciting is that, go ahead.
Fantastic to have you leading us into a way to begin to get our hands on and involved in a community that's building foundation models and doing machine learning. Alex, this is what this podcast is all about. Thanks.
Awesome. I wanted to say my colleague Eric Check. What I guess is really exciting is the idea of using Marin outside of large language models and other domains of science. And my colleague Eric has just gone through this process, and it's all like in the open for reproducing one of his ML models, which is a plant caduceus, or the idea of like, could Marin, the infrastructure, immediately be used for understanding plant DNA or DNA more generally? So here he had an issue for reproducing plant caduceus, and which is an ML model that tries to understand plant DNA and like especially maize crops. And I guess what I'm really excited about is in the potential that with something like Marin, whether it's specifically Marin or another type of framework, that more and more development processes for science would be totally opened up, where it's not just a matter of the code being open source, but the entire development process, like inclusion of people in the experiment, the access to compute, the tracking of projects and what's going on in priorities are totally open and inviting and centering a community. I guess I'm really excited about having that level of like open source community and open source like effectiveness being applied to other domains of science. I've mentioned Czar on this. Mentioned Czar a lot on this.
I've still got
recording.
my phone with
I know. I'm
stickers on it.
I'm a big fan of Czar, but Czar as a data format started in the biological community, like started as a bioinformatics format for large biorasters, and then kind of eventually went over to climate and weather, and now is going over into geospatial. And I guess I'm really excited. I see a parallel here too, where we have stuff in one area of tech like large language models, and then maybe kind of the next area of science that it may focus on is DNA or like bioinformatics, and it'd be really cool if like the next thing that it goes and is useful for is like climate and weather and so on and so forth, in other domains of science.
So what's bubbling up on LinkedIn lately, but I've seen it for most of the year really, is the likes of Jan LeCun, who I think has just left Meta, talking about world models. I think Fei Lin from World Labs has also been leading the charge in the next way that we iterate on AI, taking it beyond LLMs to world models. Is there a link here?
Yeah, I'm not an expert in world models, so I won't make any claims about what they look like or how they're used. I know Jan LeCun in particular has JEPAs, which are joint embedding predictive systems that have been really interesting. And I think he thinks that they're a good successor to LLMs for getting past their autoregressive curse. I could say more about model architectures that would be really useful kind of towards that end. I think that are really interesting. Like, actually Eric also, he's helped research in, or his collaborators have done research in diffusion language models, which is, I think, one of the limits of Jan LeCun has specifically talked about with large language models. I can't say Marin in particular is a solution to this. I think it maybe is a more of a traditional language model. But it's still exciting. I think if you were really curious about using the latest technique for building world models as something distinct from large language models, you could probably use Marin as a starting point to go and build that and do that experiment should it be agreed upon by the community.
Perfect, amazing. So great to have you pointing us in the direction of this community for those who want to continue on with this journey. Yeah, great.
Cool. I did want to say that one of the, I just want to relate it back to kind of what I'm working on right now. This is not a project that I've worked on, but my collaborators, Laura's at NYU and Abigail's at MIT, and we're all part of the M squared lines community. That's what this diagram is right here. And we just had a release, the community had a release in partnership with AI2, the Allen Institute of AI, to create something called Samudrace. And Samudrace is it's a coupled atmospheric and ocean and sea ice model. And Samudrace, I work on a team building Samudra, for example, which is the oceans component, and ACE is the atmospheric climate emulator. That's what ACE stands for. And these components have been built out somewhat in the open. I don't think the development process has been totally open, although it has been, you could probably find a GitHub issue, at least in like the ACE project, and maybe make a contribution. Marin is quite a gold standard to follow, but I think this is still like, especially the work of AI2 is incredibly open. But like through open source code, we're able to do something really crazy, like simulate 800 years of the climate in one day with one GPU. Is like one of the successes of Samudrace. So that's what you're seeing here is like a climate simulation through this collaboration with our partners of at a decent resolution. This is a temperature simulation going like really quickly forward in time.
So this is
And
month by month. Is it the animation for those who are listening to the podcast is at 320? Is that year 323 now, and then month by month?
that's what it looks like. Yeah.
Okay,
Um,
amazing. And when you say one GPU, I mean, what I think of is, my beige desktop computer. Is that what you mean by a GPU, or are you talking about a Jensen Huang GPU, which is a data center type situation?
I mean, like a data center GPU. I think this might have been an A100 or an H100, which is like a GPU designed for machine learning.
Gotcha. Okay. So this is
But
a significant expense still for the average. This is, I don't know, computer science lab in a university, that kind of a budget that you'd need to pay
well,
for that.
yes, probably these were probably run on university resources, but you could go out there and rent a computer for a day, probably pretty inexpensively. It might be like $3 an hour or $5 an hour
Really?
for 24 hours via like, Lambda Labs or AWS or GCP. So yes, it requires some
Nice.
pretty beefy hardware, but like in theory, yeah, you could rent these things. And it probably wouldn't be one day, 800 years in one day, but if you had like probably a normal gaming laptop, you probably could, with some elbow grease, configure it to run a simulation like this. And I think this is all that I had prepared for my presentation. But I guess, I love the idea of a potential of an open development process for building climate models, where, these are two different projects, kind of building independently, releasing things in the open, and then like coupling them together. And I think I'm really all for just making the entire development of like climate and weather models more open and more collaborative fundamentally. And I'm really excited. I think that's something that Open Athena wants to help make possible and make more common.
Okay, so tell us a bit more about the Open Athena team. You said they were all-star cast.
We have a lot of experienced machine learning scientists who have a mixture of like industry, software engineering experience, and machine learning experience. And kind of the thesis of Open Athena is to partner or to help provide top academic labs researching fields of science the like software engineering skill experience or like technical experience to try to scale and build more ambitious like large scale AI models for fields of science. I think academia in general is really talented with people with like really great modeling ideas and domain expertise and often data sets that are really essential to pioneering science. But there's still like for various reasons of like incentive structures, no fault of anyone. There's still like a missing skill gap of like compared to industry for getting people's like industrial grade engineering experience, especially scientific engineering experience, and bringing it to academia. So yeah, I'm not sure how much I can say about each other's projects. We work with a lot of top universities, primarily in the U.S. East Coast, but we're moving. Stanford's one of our first collaborations on the West Coast, and we may be moving to more places sometime soon.
Amazing. It sounds like you're the ML ops team that comes in and saves the day for all of these highly theoretical scientists who have heard about machine learning and want to properly leverage it.
Right. That's the dream. That's I think the goal.
Okay. So is it all climate related stuff? Is it all to do with weather prediction? You gave an example to do with DNA. Are you branching out into other applications?
Yeah, I think we work. It's really funny. I say that like we do like a cell or smaller, except for us, which is the entire ocean system. And I think projects that we work on are related to like protein folding and plant DNA and material science. Primarily, are a lot of the other projects. Large language modeling, I guess. I'm not sure of the scale of like language necessarily in terms of the physical system. And then we're working on an ocean physics emulator, trying to trying to predict ocean states over long periods of time and making it way more computationally efficient.
Okay, and the entire global community could access the output of your work and the progress of your work via the Marin community. Is that right? Like
Not
it's
yet.
not that. Okay.
Not yet. Marin is not where our models are hosted. I think we're really I think maybe that would be a dream that we'd accomplish one day, but it's not the case now because we're really trying to be good partners with our academic labs and really just trying to help help make progress in ways the labs want to define and set for themselves. So it's we're not necessarily like a Marin company per se, but we will like for us it makes sense to we work with a code base that was already existing and we like made it better, which Marin is a JAX project, for instance. We're operating in PyTorch, and I think it's similar for other labs that we partner with too. So we're really trying to start where labs are already operating in and like just really improve their workflows and system performance and ML model capability. Openness is ultimately a goal to try to shift to like open development models.
Okay. And so you partner with academic institutions. So do they fund you?
We're philanthropically funded. Open Athena is philanthropically funded.
Okay. All right. So really nice to see that, there are some enlightened folks out there that, have accumulated this money and have found what can I say, an impactful way to deploy it. There's the human aspect here, Alex. I just want to say how generous you are with your time. You are so approachable. You are the opposite, I think, of what many people have in their mind of a hard-nosed computer scientist type who wouldn't want to spend the time of day with an average person on the street. You are so generous, and I think really humanize this mysterious, almost priestly profession related to machine learning, things like that. So there's that to say, Alex, and I really appreciate it. You've spent so much time, you're so patient and about all the questions and remarks I had holding up the progress of your presentation, stringing it out for 3 episodes.
The point of the presentation is to have the questions, more so than anything else. So thank you for asking those questions. I really appreciate how engaged you were in general, and thank you for, letting me, I guess, talk about things I care about, but often, are very intimidating to people, and I'm happy to make space for all that.
Yeah. So as I said in our discussions on LinkedIn before we recorded, the podcast is about broadcasting in geospatial. It's about foundation models in geospatial. It's about data engineering in geospatial. And then it's a collecting point for all of this effort, which is the stock market. And that's how regular folk, those without, institutional money, can somehow ride the wave of all of this effort that you've been describing. And then I said the last point of this podcast is the human rights outcomes of all of this effort. Because for heaven's sake, if the likes of yourself and all of the collective academic institutions, ultimately all of that effort and knowledge funnels down to some sort of commercial effort, and it would be a grave pity if the outcome was bad for underprivileged people. So maybe a good place to end on, actually, is whether or not there are discussions about this kind of thing at Open Athena. I'll just, any reflections personally that you have in terms of what guides you.
Well, yeah, I think I'm particularly incredibly grateful to be at Open Athena, because I think its mission more or less is to do basic research that it could potentially help lots and lots of people in like really, totally different fields, whether it's like material science, creating a new Haber-Bosch process to like reduce the pollution aspects of growing our food, to making it plant crop yields more productive, and all these really important, giving people more adaptability information for sea level rise. We really want to take on these really great scientific challenges, not for a commercial end, but for the sake of like creating better creating better fundamental research that could really help a lot of people that people would want to build a foundation on. And I think that really goes to the thesis of this company, and it's a nonprofit. I keep on saying company, like I'm used to working in a commercial company, but that's the whole thesis of this nonprofit. And I'm really a privilege to get to go to work every day and work with all my great colleagues.
Yeah, okay. So there's a reflection of similar themes then from Development Seed when I did an episode with Kevin Bullock. So nice to collect up another bunch of kind folk that are taking the time to devote themselves to these grand challenges, Alex. So another thing here, in the end, we want to unleash the human spirit, ingenuity, innovation, and dedication. So I think it's so important to have at least somewhere, some organization where people can go, where it's assured that you can unleash yourself So yeah, thanks for giving us another example of an organization like that, Alex.
Thanks. Yeah, thanks for having me, Will. And yeah, can't wait to talk more soon.